In our next lesson on oxidative phosphorylation from Chapter 15, we want to look at proton motive force. In our last lesson, we talked about the fact that multiple components to our chain give us multiple proton pumping stations. And so we can store more of the energy in the form of that gradient, and we lose less of that energy. Let's look more particularly at that. Remember, as we pass those electrons with the reduction potentials from each component in our chain, from complex 1, starting with NADH, through complex 3 to complex 4, so in other words, our electrons are going from NADH to O2. In each step of that process, we release free energy. So the total free energy released in the transfer of those two electrons down an electron transport chain is about 218 kilojoules per mole. Each phosphorylation of ADP to form ATP requires the input of about 30 kilojoules per mole. So by simply passing those two electrons down the electron transport chain, we can actually have enough energy to create several molecules of ATP. This model is referred to as the chemiosmotic model. It was first proposed by Peter Mitchell, and it in essence states that energy is stored in our proton battery, as it were, and that's what's going to be used to drive ATP synthesis. So the chemi part of this has to do with the fact that we're talking about a chemical reaction to synthesize ATP. It's osmotic in that it's driven by transport. In this case, the transport of protons. We're going to flow protons back into the matrix, and that's going to give us the energy we need to make the ATP. The overall reaction is given at the bottom of the screen here. We're going to phosphorylate ADP to form ATP, and we're going to use the translocation of protons from the P side to the N side to drive that process. The enzyme that does this for us is called an ATP synthase, and because it's coupled so tightly with electron transport, it's sometimes called complex 5, as illustrated here. So this imbalance of protons actually represents a source of free energy. It's called proton motive force, and we can use that to drive the activity of the enzyme that makes ATP synthase. Remember, the concentration of protons is high outside the matrix. So with regard to this proton gradient, there are actually two aspects to it. One has to do with the chemical imbalance in the concentrations, and that's pictured on the left of our screen here. So the free energy represented in that chemical balance is simply RT times the natural log of that difference in concentration outside over inside for those protons. However, since those protons also carry a charge, then there's also an electrical imbalance, and that's pictured on the right here. In that case, that aspect is simply delta G is equal to ZF delta psi. In other words, it's directly related to that membrane potential associated with the difference in charge. So if we combine those two together, we can see there are two aspects of this proton gradient. One having to do with the chemical imbalance due to the concentration difference, and one having to do with the charge difference. So the question is, how much can we actually store in this proton gradient? Well, as we just saw, if we oxidize 1 mole of NADH, it releases about 220 kilojoules per mole of energy. We're going to pump 10 protons in the process, and that energy is about 200 kilojoules. And so in other words, we only lose about 10% of that energy, and that's a pretty good recovery. So remember, if we pumped fewer protons, we'd store less of that as energy, we'd lose more as heat. In our next video lesson, we want to look at how the energy that we've stored in that proton gradient can be used to synthesize ATP, and we'll look at the structure and mechanism of that enzyme.